Okay, so now to take a look at part B. So again, given this differential equation, there is a value of b for which y equals 2x plus b is a solution of the differential equation. They want you to find the value for b and justify your answer. So y is equal to 2x plus b. Again, that's your slope-intercept form. So we know that 2 is your slope. So then the dy dx has to be equal to 2 when we're trying to figure out what the b value is going to have to be. So they're giving me the differential equation dy dx is equal to 2y minus 4x. Well, we know that y is equal to 2x plus b. So by substitution, I can take out the y and replace it with a 2x plus b. So dy dx is equal to 2 times 2x plus b minus 4x. So I distribute. Dy dx is equal to 4x plus 2b minus 4x. So then dy dx is equal to 2b. So what is the value of my dy dx for this particular equation? It is 2. So 2 is equal to 2b, so b is going to be equal to 1. So now take a look at part C. So g is a function that satisfies a differential equation with initial condition 0, 0. It appears at the slope field that g has a maximum at 0, 0. Because you can see how the curves are kind of curved. It goes up and then it's going to curve back down. Using the differential equation, use the second derivative test to show that this is so. So first of all, we've got to verify that we do have a local extremum at 0, 0. So we know locus extremum is going to occur when your dy dx is equal to 0. So that's where your local extremum occurs. So this is where my 2y minus 4x, again, dy dx is equal to 2y minus 4x. So now to check to see if I do have a local extremum at 0, 0, I want to find the value of this derivative at 0, 0 and verify that it is indeed equal to 0. So 2y minus 4x, set my derivative equal to 0. Plug in 0, 0, 2 times 0 minus 4 times 0 is equal to 0. So I do indeed have a local extremum at 0, 0. So now to use the second derivative test, I want to check to see if it's whether going to be concave up or concave down to see if I have a local max or a local min at 0, 0. So then to find my second derivative, I'm going to use my implicit differentiation, so that's going to be 2 times dy dx minus 4. So again, plug in your first derivative into the second derivative. It gives me 2 times 2y minus 4x minus 4. So then my second derivative is going to be 4y minus 8x minus 4. So now what I want to do is I want to find the value of my second derivative at the point 0, 0. So I end up with 4 times 0 minus 8 times 0 minus 4, so that gives me negative 4. So the value of my second derivative is negative. So since g double prime of 0, 0 is less than 0, that tells me that we are concave down at the point 0, 0. So since I'm concave down, then that tells me at 0, 0, I have a local maximum at 0, 0. All right, so now let's talk about how we can actually match slope fields with the differential equations. So when you're doing a matching problem and you want to match a slope field with a particular equation, here are some guidelines to follow. If the slopes are the same vertically, then you know the differential equation is only going to have x's in it. So that's what I always look for. Or if the slopes are the same horizontally, then the differential equation only has y's. If the slopes have a combination of slopes horizontally and vertically, then the differential equation has both x's and y's. And when this happens, what you're going to do is you're going to choose one particular point. and substitute into the differential equation to find the slope at that particular point. Find the point on the graph and choose the one that matches it. If there is more than one graph that has the slope, then choose another point. So in other words, if you've got a combination, you've just got to look at the different points and plug them in and see. So for example, here are 4 slope fields, 4 different equations. So notice option number 1, option number 3 are the only 2 where option 1 has just an x in it, number 3 has just a y in it. So when I look at one, when I want to match the slope field for the first example, what I want to do, since this differential equation only has x's in it, I want to look at my slope fields and notice which ones have the same slopes going vertically. So the only slope field that has the same slopes going vertically is option B. When you look at number 3, notice you have just a y in this differential equation. So you want to look to see which of your slope fields have the same slopes horizontally. So the only one that has the same slopes going horizontally, notice, is option D. So this has to be D. Now when I look at 2 and 4, I'm going to zero in on option 4. Notice, if I have a y coordinate that's equal to 0, this slope is going to be undefined. So I know it's undefined at y equals 0. And the slopes are going to be 0, which means they're horizontal. Or what you can do is look to see when you have a slope of 1. So you have a combination. So sometimes when I see a fraction, I look to see where it's going to be undefined or where it's going to be equal to 0 to see where I'll have the horizontal. So for example, if you take a look right here, so my choices left remaining are A and C. So notice right here on my slope field for option A, notice there is nothing going along the x-axis, whereas here in C, I do. Remember, it's going to be undefined when y is equal to 0. So this one has to be choice A. In choice C, x minus y, again, when x is 1, y is 1, I know that the slope field is going to have to be 0. So at 1, 1, I should have a horizontal tangent line. At 2, 2, I will have a horizontal tangent line. 3, 3, I will have a horizontal tangent line. So this has to be C. Okay? So I would see horizontal tangent lines kind of help me match the text as well. So that is slope fields.